Most of the time in introductory physics, we assume that air resistance is negligible. But this video will give you a small glimpse into real-world physics, where all of a sudden air resistance is no longer negligible. Air resistance is an example of something we call a drag force, which occurs whenever there is a relative velocity between a fluid and a body. A fluid is anything that can flow. So you could have drag force in water, or in air, or really in anything that has that viscous nature. It's important to know that a drag force always opposes motion. This means it always acts in the opposite direction of motion. Or, really, it's the direction of the fluid flow relative to the object. For the purpose of our course, we will only deal with situations that follow under these examples. So we're only going to deal with things where the fluid is air. We'll only deal with situations where the body is blunt rather than slender. Think of like a baseball, not a needle. And we'll only deal with times when the relative motion is fast enough so that the air becomes turbulent behind the body. What that means is that as the air flows behind the object, let's say that our object is a baseball and it's going to the right here. As the air comes behind it, it ends up making kind of circular motions due to the way that it splits around the ball. So that would be the turbulence that we're talking about here. And that'll be the case for majority of objects. So when we satisfy these three conditions, we're able to write an equation for the drag force, kind of a general equation for it. And that equation is D, which represents the drag force, is equal to 1/2 C. C is something called the drag coefficient, which is typically experimentally found, times rho, that's the density of air. Again, something you can look up. This varies with temperature and also with distance from the surface of the earth. Times A, that's the effective cross-sectional area. In other words, it's the area of our object that is perpendicular to the velocity. So if we went to our baseball example, we would look at an area of a circle like this, perpendicular to the velocity. The circle would have the diameter of the baseball. And then times v squared, or the magnitude of the velocity squared. So you'll see that the drag force varies as an object speeds up or slows down, which should make some sense. You all have experienced the drag force before if you've ever stuck your hand out a window. If you have your hand flat so that the air is hitting the palm of your hand, there's a lot of drag force there. It's even more drag force if you're on the highway doing that versus if you're on a road going 35 miles per hour. Now, if you were to turn your hand sideways, you'd notice that there's not as much drag because the cross-sectional area decreases. Let's look at another example of drag force. There's a myth that says that if you drop a penny from the Empire State Building, it could kill someone if it were to land on them at the bottom. That's why a lot of tall buildings, you can't go out to the outside. But we're going to look and see if that's actually realistic. Could a penny dropped from the Empire State Building kill someone? We'll start by looking at the forces on that penny. Well, if we were to draw a free body diagram for that penny, we know that we'd have the force of gravity acting downward. And now, of course, because we are dealing with drag force, if the penny's going downward, we have a drag force acting upward. writing a net force equation for this would yield the equation D minus Fg equals ma. And we know that it's accelerating downward, so really we could say negative ma. Now, as our penny speeds up, we know that the drag force gets larger and larger and larger. So, because that drag force gets larger and larger and larger, eventually the acceleration becomes zero, because the drag force will get to a point where it is equal to the force of gravity. It would never go above the force of gravity because the acceleration is zero, so the speed becomes constant. We have a special name for that speed. That speed is called terminal velocity. When an object reaches terminal velocity, it is no longer speeding up or slowing down. It is all of a sudden going at the same constant speed, because again, the drag force is equal in magnitude to the gravitational force. Let's derive an equation for that terminal velocity. So, for starters, we know that the drag force is equal to 1/2 c rho a v squared, and we know that that has to be equal in magnitude to the gravitational force, or m times g. Since we're trying to solve for velocity, and I'll actually put a t on there so that we know that we're solving for terminal velocity, I would end up multiplying both sides of my equation by 2 and dividing both sides of my equation by c rho a, and then I'd have to take the square root. This equation can be used to solve for the terminal velocity of any object, including that of our penny falling off the Empire State Building. So, if we really want to know what that terminal velocity is, we're going to have to look up some values. Mainly, we're going to need to look up what the mass of a penny is, what the effective drag coefficient of a penny is, the average density of air, and the cross-sectional area of a penny. Now, we can't get quite to real-world physics because we know when we drop something, it usually doesn't drop just straight down, it usually spins. And that complicates things a whole lot. So we're going to make some a little bit unrealistic assumptions, but it'll be okay. Our first unrealistic assumption, and really our main one, is that that penny is going to fall so that the flat side of the penny is parallel with the ground. That'll help us follow along with those 3 rules that we had. I will resort to Google to come up with the mass of the penny, the coefficient, the air density, and the area. Google tells me that the mass of a penny that has been produced after 1982 is about 2.5 grams. So, of course, we have to convert that to kilograms. So, 0.0025 kilograms. We know G is 9.8 meters per second squared. Notice the lack of a vector symbol, so I'm not plugging in a negative sign with that. The drag coefficient of a circular disc, like a penny, is approximately 1.17. Again, it's a coefficient, so it has no units. Air density at sea level, which really doesn't change much from the top of the Empire State Building to the bottom, is approximately 1.225 kilograms per meter cubed. And then as far as area goes, we need to calculate the area of a circle. Our penny has a diameter of approximately 19 millimeters. We know that the area of a circle is pi r squared. So plugging in the 19 millimeters taking that in half to find the radius, squaring it and multiplying by pi, ends up yielding an area of approximately 0.00028 meters squared. Okay, so I plug all of this into a calculator to find out exactly how fast it could possibly be going, which yields a speed of approximately 11 meters per second. 11 meters per second is about 25 miles per hour. That's pretty slow, actually. You could probably throw a penny at 25 miles per hour and hit someone, and I don't think it would even cause a bruise. Now, in reality, because the penny rotates, it does actually get to move a bit faster than 11 meters per second, or 25 miles per hour. But, moral of the story is, it's not going to move fast enough to actually kill anyone. In class, we'll do some more examples with drag force, and we'll see how we can use it along with a net force equation to calculate an object's speed at any given point in time.